No, he needs to tell you that the first time. So the way you know I expected you to
Alright, well, while my computer decides to reboot itself because of updates, how are you guys doing?
Great.
Glad to hear.
I speak very well.
I'm sleepy, but that's usual.
Sleep.
Just busy, making sure everything's ready for test week next week. How are you guys? I asked how you guys are feeling. Does anyone have any questions about anything at all before we get started today?
Do you know, so those are like our final exams time. Do you know when we'll get our like scores back, or do we have to check like Banner to like see your final?
So the last exam day is on Friday. In a second I can check when grades are due by, which means I would have them graded by that point. Now, grades going out is the normal system by which you'd see things. However, your final average is not necessarily your exam score. So by the time that grades go out, if you want to know like specifically your exam score, you can email me about that and I'd tell you. In a sec, I'll check exactly what date that would be though, just as the guaranteed latest point I have to have them finished by. Does that answer the question? Okay. At the top of my head, Thursday's I think the start of the exams, meaning that they would also be given on Monday and Tuesday. I'd expect grades to be due by the following Friday. So I would definitely have them finished by then via contractual obligation.
How many finals do you have?
But my computer is taking longer to start up than usual today because it decided to update itself against my permission. So I will get you that information in a sec. Any other questions for right now? Okay. Well,
Isn't the
calendar.
Is this what
Yeah, this semester final grades are due by the morning of Friday, December 15th. So for that reason, I would expect myself to be done grading by Thursday night after the exams. I could finish sooner, but that would be the absolute latest. All right. Last time we began talking about chapter 9. The main concepts we addressed on Monday were a review of density, the definition of pressure. Pressure is force exerted over a surface area. Looked at how to calculate pressure at a depth within a fluid, especially since we are always submerged at a depth within a fluid within Earth's atmosphere. And also the source and the definition of buoyant force, which is to say you are submerged in a fluid, the fluid exerts a net force upwards because the inward upward pointing force exerted by the fluid on you beneath you is stronger than the inward downward pointing force on the top of you by the fluid because the pressure increases with depth, therefore the force increases with depth. Related fact to that, actually, I should mention this on Monday. Have any of you ever been to the Hoover Dam? So, the dam itself, and most dams do the same thing, it's just the Hoover Dam is bigger, so it's easier to see. So these are some shots of the dam itself. On one side of the wall, it's flat all the way down. But on the other side of the wall, notice how it curves upward? That's because pressure increases with depth. The water pressure caused by the water in the lower part of the dam is bigger than the water pressure at the upper part of the dam. So they literally built it outwards like this to reinforce the bottom in comparison to the top. So if you ever see a dam shaped like this is why. How do you guys feel about all the stuff, all the formulas and concepts from Monday? Because our goal for today is to practice them a bit more, maybe talk about one additional thing between today and Friday. Yes?
So, is there going to be one question on the test about chapter 9?
One, maybe two tops.
Okay.
Yeah, I would expect one, if I'm being honest.
Okay.
I'm finalizing it today, and that is the current expectation in this draft.
Do you want me
Okay. Yes.
to? Caleb asked how many is on the test.
Any questions?
Yeah.
9.
Yeah.
So, same as last test. The first page will involve a couple concept questions. So of the 9, about 2 of them don't necessarily require any math. And then 7 math questions that I am writing as math questions, but you can still earn points by writing out what you understand about the situation. And like last time, it'll mention, each question will tell you how many points it's worth. Does that answer yours and or Caleb's question?
It answers his question.
Alright. So. One sec. So, let's practice the concepts we covered last time. Most especially buoyant force, by looking at an application of buoyant force in submarines. The way that these machines tend to work is they sink by controlling their density. They are able to pull seawater into holding tanks, and seawater is more dense than the air that is normally in those tanks, or possibly just the empty space that is in those tanks. And so when they pull seawater into the tanks, that has the net effect of increasing the overall density of the ship, causing it to sink. If the density increases, it's likely to become more dense than water, and its weight is going to increase. Thereby, the weight would be bigger than buoyant force, and it would sink. When they want to rise, they eject that seawater out from the tanks, driving down the net density of the submarine, driving down its weight, and then causing it to rise until buoyant force and gravity equalizes. This particular submarine has a mass, a normal empty holding tank mass, of 43,000 kilograms. So these things are heavy. They are made out of solid metal after all. And we are going to examine just the base mechanics of it floating. Here is my very cartoonish submarine. Note that like most boats, most of it is still underwater even when it's surfaced. That'll become relevant in a minute. Assuming that the mass of the submarine, while its holding tanks are empty, is 43,000 kilograms, what must the current buoyant force acting on this ship be?
Can you repeat that?
Yes. Submarine is currently floating on the water's surface. 1/5 of it is sticking out of the water, but that's, like the upper deck where you can get on and off. It's currently floating. It is on the water surface, as stationary as you can be in the ocean. Its mass is 43,000 kilograms. Given this information, what must the current buoyant force acting on it be?
Can you repeat the question?
Yes. Submarine is floating on the water's surface. Its mass is 43,000 kilograms. It is floating stationary on the water's surface. What must the buoyant force acting on the submarine be?
Are we supposed to find volume?
Eventually.
I'm confused about how to do that.
Okay. I know some of the homework questions involve double checking, like how to find the volume of a certain shape.
That's,
There's at least one question involving a sphere where that's necessary.
That one's easy, it's just like, if I don't like the shape, I don't.
Okay, yeah, we can double check those.
Wait, isn't the force of buoyancy equal to the negative force of gravity?
Correct. If something is floating by itself, unassisted, and there's only two forces on it, which is to say, buoyancy up and gravity down, and it is floating, which is to say, not accelerating, staying still, the buoyant force should be equal and opposite to gravity because they have to add up to 0. So again, the rule is, floating unassisted, if these are the only two forces adding up to 0, they must be equal and opposite. So, again, if you know the weight of an object and it is floating, the buoyant force, whatever vertical forces are acting on it, must be enough to counteract that to hold it in place. So, we can actually just find its weight using gravity, and the buoyant force should be equal to that total. And then we can use that in the next part. So, net force equals mass times acceleration. Ship's not accelerating, so this whole side is 0. There's only two forces adding up to 0. That means that they must be equal and opposite to each other. Buoyant force must be equal and opposite to gravity on this particular vessel. Its weight is equal to its mass times 9.8. This extra negative sign cancels out the negative sign in the G, and so we will get a very big weight and therefore a very big buoyant force, the needed buoyant force to hold up this particular tub of metal. This submarine, with its tanks empty, weighs 421,400 newtons. Trying to compare that to pounds real quick. It'd be at least 100,000 pounds. So 50 tons-ish, give or take. Submarines and most boats are very heavy, so they don't float because they're light, they float because they are able to properly weaponize the principle of buoyant force. Very heavy, and yet it floats regardless. That's because it is able, based on its shape and its volume, to generate the required amount of buoyant force to negate its own weight. How do you feel on the first part? All right. So, its weight is this number down, buoyant force must be this number up if the two cancel out. So that is the buoyant force on the ship to be holding in place. Next question then, if only 1/5 of the submarine is exposed when it is floating, what is the volume of the submarine that is under water? Any thoughts? Yes.
What if we just do, well, I was gonna say, what if we just do like the volume divided by 2, like the volume of the submarine divided by 2?
Well,
Or
what is the
divided by
volume?
5, divided by 5.
What is the volume of the submarine?
Can't you just like set the force of buoyancy equal to the density times x times gravity?
Yes, you can. We have already figured out buoyant force in a roundabout way. And that means we can plug it back into the buoyant force formula to figure out the required amount of ship that is underwater to make this thing float. So, our answer to part 1, again, that answer is the buoyant force. So that's what we're plugging in here. Next is density. Density of the fluid, and this thing is floating in seawater. So we're going to plug in the density of seawater listed above. It is slightly more dense than fresh water, so it's slightly easier to float in salt water than it is in fresh water. That's another thing that helps these things float. I guess you don't see as many huge ships in fresh water as you do in seawater. Next is volume object, specifically the submerged portion of it. So this number will answer the question of how much boat is underwater, but note that that number is not going to be the entire volume because the top fifth is exposed. So that number is the submerged portion, which answers what we're looking for here, but it's not the entire volume of the entire tub. And lastly, magnitude of gravity. Does anyone disagree with about 42 meters cubed? All right. Now that is the volume under the water, and it is functionally a cramped living space. And 42 meters cubed isn't tiny, but it's less than one would like to be able to stretch out properly. A meter cubed, just for context, meter by meter by meter. So 42 of those cubes stacked into a boxy submarine shape, basically. But a lot of that space is taken up by metal and parts, and it's not all living space. So that is how much ship you need under the water. Questions? All right. Now, briefly, I'd like to compare that to the amounts above the water. That is the submerged portion, and that would have to be 4/5 of the entire sub's volume, right? If 1/5 is still above the surface. So, multiply that by 5/4. That would tell us the whole volume of the entire submarine. That would be about 52.44 meters cubed. So that's the entire sub. And 1/5 of that, and I'll label this. Which means the amount of sub above the water's surface is 10.49 meters cubed. So, whole thing, just the part above the surface. I'm only pointing this out to fully demonstrate that most ships, if it's floating on the water surface, needs a pretty major chunk of itself underneath the water in order to generate the buoyant force required to float. Especially big ships made out of metal, which, you know, is more dense than water. You know, the metal doesn't want to float, you have to force it to by increasing its volume. You take the metal, you build it into a hull that doesn't have any holes in it, and it displaces more volume of water that way. For as much ship as you see above the water's surface, there's a decent chance that there's more of it under the water's surface if it's a very big, heavy vessel. Same with the iceberg, same with the Titanic, come to think of it. More of it was under the water than above it. Questions for right now? All right. You asked quickly about homework, and I kind of want to look at some of those questions to point some of these out.
I was looking at number
3. All right. So we'll just look at homework kind of as a sample. Block of solid lead sits on a flat level shelf. Lead has a certain density. The mass of the object is so and so. Okay. So I think to address your earlier question, technically I don't think you need to know the exact shape in this particular one. Because what it's saying here is, well, and actually I suppose not everyone has lead, but you have a box made of something. You know the density of that material and its mass. So by definition of density, you could find its volume. If density equals mass over volume.
Yeah, that's what I did.
Oh. I didn't like that? Okay.
It could just be.
I've had some issues with rounding with WebAssign recently. Like some students would round to a completely reasonable place and WebAssign says, no, you have to round here, and that makes the answer like more than 10% difference somehow.
Yeah, I guess it could be 0.002, because I got 0.00185, but I just kept rounding up to 8, so that might have been the problem.
Alright. Yeah, I can specifically look at yours later, if you remind me. Any other questions for right now? Alright. Well, I told you chapter 9 was going to be a short one. We covered pretty much all the concepts contained within it except one. There's one last little thing I want to talk about. This will be the last new thing that I mentioned before the test. And really I just find this useful. Well, rewind. One last thing I want to talk about, and that'll be where we kind of end today on, and we'll pick up on Friday, reviewing all of chapter 9 as a whole, and then moving into test prep, talking about the practice tests and things like that. We have defined pressure as force over area, over surface area. Meaning that a certain amount of pressure is going to create a certain amount of force on a certain surface area. So, say atmospheric pressure, for example, will exert more force on something that has a bigger surface area. Earth has a pretty big surface area, so our atmosphere is actually exerting a non-insignificant amount of force on the planet, but smaller object, the same pressure generates less force because it has less surface area. What I find interesting is, you can take a system, and I'm going to draw like an oddly shaped object here for a second. Consider this to be like a helium tank that you'd get at a party store. You know what? Rewind. I'm going to draw it a little closer to the actual shape you get. Tank of helium. The gas inside this tank is pressurized, meaning that the pressure inside is very big. There's a certain pressure and it is going to exert that pressure and therefore force on the interior surface area of every single wall of this container. And that's why when you open the valve, it rushes out, because it's pushing out against every single wall, and if you give it an exit, it's going to push out and exit through that hole. So that's why pressurized containers can be dangerous. And every different side of this container has a slightly different surface area. Namely, I'd like to compare the flat bottom side, because most of these tanks have a flat edge to sit on, to the upper part of the top. There's usually a valve up there, and I'm just kind of extrapolating that general shape. I kind of shaped it like a soda bottle for simplicity's sake. The top part of that valve, if we just consider it to be flat, has a smaller surface area than the bottom of the valve. It's the bottom of the container. And so even though it's the same pressure throughout the entire system, the force on the bottom is going to be bigger than the force on the top because of the difference in surface area. And this is not only true of systems like this. As long as pressure across an entire system is constant, the forces on either side might be different if the surface areas of different sides of a system are different. And that's where the notion of Pascal's principle comes in. This is the idea that a pressurized system will have the same pressure acting throughout every part of it, but even if the pressures on two sides are equal, you know, the pressures acting on two different parts of a vessel or of a system are constant, that does not necessarily mean that the force is acting with the same strength on different surface areas of the same system. So even though pressure 1 equals pressure 2, it's the same constant pressure throughout the entirety of this vessel, you can still get the same pressure with a different force over a different surface area. So what Pascal's principle tells us is the forces might not be the same on all the different areas, but the pressures will still be constant throughout the entire pressurized system. Question is, what do we do with this information? Although, before I address that question, does this notion make sense so far? All right. Now, this fact is surprisingly useful if you are, say, an engineer or even perhaps an automotive enthusiast, because it's the system that allows hydraulics to work. Because it's not just gas that is pressurized, you can also pressurize liquids. And liquids are convenient because they are fluids, they exhibit fluid tendencies, but they have definite volume at a certain temperature, meaning you can't really compress water all that much. If you push inward on an amount of water, it's not going to get any smaller, it's just going to flow out of the way. Same is true of most liquids. Gases, they are fluid, they have non-definite shape, but they also have non-definite volume, meaning you can compress a gas to a smaller size if you pressurize it. And that's the entire reason that helium tanks and other gas tanks work, is gases can be compressed, but liquids can't, or at least it's a lot harder to do so. And for that reason, if you create a system of pressurized liquid, you can exert a force on one side of it and have that force transfer to the other side of the system. This is basically a pipe system, and this is specifically being utilized in, say, a car shop. Because when you take a car in to get serviced, usually, depending on what the problem is, they're going to lift it high up so they can see everything underneath it, right? Cars are heavy. It takes a lot of force to be able to do that. And people have noticed that scientists have been able to make use of this phenomenon to help get the car physically elevated. Underneath the car shop as a whole, is a liquid reservoir. And that liquid is pressurized, meaning that if you exert pressure on one side of it, it's going to exert that whole pressure over the entire system. The pressure on one side will equal the pressure on the other. But they very specifically made the different sides of the container have different surface areas, meaning that even for that same pressure, a force on this side of the vessel won't be the same as the force on the other side of the vessel. Meaning that you can exert a teeny tiny force on a teeny tiny surface area piston or valve over here, and that's going to cause liquid to flow through and push up on the other side. And as long as the other side has a bigger surface area, you're going to get more force out of the same pressure. I'm going to try to represent this a little more three-dimensionally. I find the flat image here to be a little hard to see at times. So this is an attempt to make that image a little more three-dimensional. This side of the system, this cylinder is just physically narrower. So this flat surface area up here is simply smaller than this flat surface area over here. And each side of the system usually has a piston or some sort of a valve on it such that you can physically push down on the piston, and that's gonna push down on the fluid contained within this whole reservoir. It's gonna physically push the liquid down this cylinder into the reservoir and then up out the other. It's gonna push up on the other side of it, because that's similarly got a piston over here that is able to give as long as it's being pressed on. This is the side you put the car on. And ultimately, a machine is going to press into this valve, exerting a certain amount of force on this area, and that's gonna cause a different amount of force to come out of this area on the other side. This is the basis of a hydraulic system, which is used in cars and also a bunch of other places. If you've heard the word pneumatic, it's basically the same thing. They just figured out a way to use gas instead of liquid. And at least prior to, say, electric motors, this was one of the main ways we used to make things move. So just to kind of quickly demonstrate why this is useful. We've got a car in a car shop, and it's going to be elevated by this platform. And I just want to, let's just calculate how much force is required to lift the car on this apparatus. The car has a mass of 650 kilograms. It is sitting on top of a cylinder with a cross-sectional surface area of 2 meters squared. So that's just the area of the flat circle that is the bottom of the piston on this side. On the other side, it's a much smaller 25 centimeters squared. Car sitting over here. In order to elevate the car, something else has to push down on this side. We're just going to demonstrate the difference in the force required between the two sides. Pressure on both sides must be the same. So the force over here over that cylinder's area must be the same as equal to the force over here over this area. The area of this cylinder is 2 meters squared. And how much force is required to lift a car? Or how do you find the force required to lift a car?
Force of gravity.
Yep. So mass of the car times 9.8. And that'll tell us how much pressure is within this system to make this happen. And in turn, that'll tell us how much force we have to exert on the other cylinder to make this whole thing happen. Now the area over here is 25 centimeters squared. We want that in meters squared. So how many meters squared would 25 centimeters squared be?
25.
Almost. Because when the unit is squared, you have to convert it twice.
Jesus.
So it's actually 0.0025. Divide by 100 once, and then a second time because the unit is squared. So it's really a teeny tiny surface area. They use the smallest pistons possible on the tiny side. So, this system is able to lift a car with approximately 8 newtons of force. So, with less force than it takes to lift this thing, you could pick up a car if you had this hydraulic system to utilize. Machines like this are able to use pressure to basically amplify and multiply your force output, making life easier. And again, until the invention of electric motors and internal combustion, this is how most machines made things move. Hydraulics. Hydraulics and pneumatics. That's how trains worked. There is a downside though, and it's that this piston just has to be a lot taller than the other one. Because what's really happening here is the same volume of fluid being pushed out of one side has to go to the other. And since this side is a bigger area, it fills up more slowly than this side drains. So this side has to be super tall if it was just linear. You have to be exerting 8 newtons of force down for several hundred feet possibly. So you have to be very smart in how they build these things. Questions? Bless you. All right. Well, that's the last chapter 9 concept I wanted to show you. So that's the last new piece of learning we have before the test. We can break here for the day. On Friday, we'll review chapter 9 and then review the past couple of weeks as a whole. We'll make sure the practice test is posted by then. We can look over it on the test info stuff. Anything on your mind before we break for the day? All right. In that case, you know if you need anything, and have a great day. Yeah.
Alright, what are we going to do? Fill up first one over area.
You did not explore the